matter, it can exist in 3 states, and these 3 states are solid, liquid and gas. Now why they exist only in these 3 states? The reason behind that there are 2 opposing factors that are responsible for their behavior, that they can exist only in 3 states: solid, liquid and gas. Now what is these 2 opposing forces? These 2 opposing forces, one is intermolecular forces. Intermolecular forces, it helps to keep the molecules or atoms or ions bound to each other. So it helps to keep the molecules and atoms or ions closer to each other. Fine. And there is another opposing force, that is, now the effect will be opposite, which is thermal energy. Because when we apply heat, it tends to keep them apart by making them move faster. So because of the presence of high energy, now they will move faster, and when they will move faster, the intermolecular force that is present between the atoms or ions, that will be decreased. Okay, so that is why these 2 are opposite to each other. Now thermal energy, suppose under normal condition, that is if we consider room temperature, that is 25 degrees centigrade, under that condition some substances are in solid state, some substances are in liquid state. So temperature is fixed. Fine. Then why they are in solid state and some are in liquid state, some are in gaseous state? It is because of the intermolecular forces. So under constant temperature, that is when thermal energy is fixed, that is same, under that condition, if the intermolecular force between them is very high, then it will be solid. If it is moderate, it will be liquid, and if it is very low, then it will be acting as gaseous state. Fine. So that is the opposite effect. Similarly, if intermolecular forces we keep it same and we increase the thermal energy or decrease the thermal energy, accordingly the states will change. Fine. So depending on intermolecular force is winning over thermal energy or thermal energy is winning over intermolecular force, accordingly there may be 3 states. It may be solid, it may be liquid, or it may be gas. Now in this topic we will be interested in solid state only. Okay, what are their properties, why they are so unique from liquid and gas. So liquid and gas together, they are known as fluid. Fine. Because they can flow, but when the matter it is in solid state, they cannot flow. So we cannot say that solid state is fluid. Only liquid and gas, these 2 are fluid. Now we will see some properties of solid which make them so unique. This is definite shape. So they have particular shape which we do not see in case of liquid. You can keep liquid in any container and it will take the shape of the container. So there is no definite shape, and gas, no question of shape. Fine. Then there is definite volume. Now when we talk about volume, liquid also has definite volume, but if we consider gas, there is no definite volume. Okay. So this volume, definite volume property, it is common for solid and liquid also. Then rigidity. So that is the atoms, molecules or ions that are present in solid, they remain at fixed position and they can change their position, that is they can vibrate when temperature is high, but that is keeping the mean position fixed, only they can vibrate. Fine. So their position is fixed, so that is why they are rigid. Then high density, that is mass per unit volume, that value will be very high compared to liquid and gas. And low compressibility, so we cannot compress it at all. In compared to liquid and gas, gas is obviously highly compressible. We can keep same amount of gas in a very large volume as well as in a very small volume. And for liquid also there is some amount of compressibility, but in case of solid, compressibility is not present at all. Okay. And strong attractive force between the constituent particles. So between 2 particles there will be strong attractive force. Now these forces are intermolecular forces, and there are different types of intermolecular forces. Some are very strong, some are very weak. Okay, so depending on what type of intermolecular forces are present, this, that is the attractive force, what type of attractive force is present, there may be different types of solid. Okay, so what are these intermolecular forces? So the solids, first of all, before going to the intermolecular forces, depending on that there is some variety, but before that we will see that what about amorphous and crystalline solid. Okay, so these classification we have done on the basis of arrangement of the constituent particles. So if the arrangement is irregular, and not fixed, then we will call this type of solids as amorphous solid. And examples are glass, gels, polymers, etc. And from the picture also you can understand that there is no regular arrangement. It may happen that for a particular region, that is for a very small region, there may be some symmetry. Okay, but this is not long range order. So we cannot say that as a whole it is very regular in arrangement. So the arrangement is completely irregular. Okay, and there is another type, the solids in which constituent particles are arranged in regular manner, that is now the arrangement is highly ordered in three-dimensional network, and this network is known as lattice, and they are also called crystalline solid. So here we have example, very common example, that is table salt, NaCl, solid HF, diamond, phosphorus. Now some examples you may find that why HF, because under normal condition it is not solid. Fine, then why we are considering it? We are considering it because when it is in solid state they behave as crystal. It is true that under normal condition it is not solid, but if we make the temperature very low, obviously they can be solid. So under that condition, when HF is solid, then it behaves as crystalline substance, not amorphous. So from the picture it is clear that here the arrangements are very ordered, and you can also find that here spaces are very large, but here spaces are very small, that is packing is very tight in case of crystalline. Now the two types of solid, there are some differences. So here we have all the main points. So when it is crystalline, there is long range orderly arrangement. Okay, long range orderly arrangement of the constituents. If it is amorphous, there is also some amount of order, but that is not long range, that is short range, and random arrangement of constituents. Fine, so there is no regularity. In crystalline there is definite shape. So when there is regularity, obviously there will be definite shape, and in case of amorphous the shape is not definite. Okay, generally anisotropic in nature, but amorphous isotropic. Now what is the meaning of this anisotropic and isotropic? That you have to know. So when we say that anisotropic, now look at this crystal structure. Here we will find the anisotropy. What is this anisotropy? Suppose we are moving along A to B. So when we are moving along A to B, on left hand side you can find similar type of these black dots. Fine, but if we consider right hand side, there is this white circles. So one side there is similar kind of atoms or molecules or ions, and in the right side there is another kind of atoms or molecules or ions. So this is one condition. And now suppose we are moving along this direction, that is C to D. C to D. Now what we are seeing, that on the both side there is alternate black and white dots, black dot and white circle. So when we are considering the property along AB direction, then there is one type of property, and when we are considering CD direction, then there is another type of property, because though it is ordered, but both sides the arrangements are not same. So that is why it is anisotropic in nature, and in case of amorphous, it is isotropic like liquids, because liquids are also isotropic. Now isotropic means here, if we consider some physical property like electrical potential or refractive index, all these physical properties for amorphous solid, it is same in any direction. Now one question may arise, though there is random arrangement in amorphous, then why the properties are isotropic? It is because though there is random arrangement, but as a whole, that is if we consider the whole structure, the irregularity, it is present everywhere. So overall it cancels each other. So as a result, the property becomes similar in all direction. Okay, so but in a nutshell, what we can say, though there is irregularity in the whole amorphous solid, still as it cancels each other if we consider the overall structure. So that is why ultimately these properties, they become same in all the directions. But if it is crystalline, then because of this difference that we have seen here, that is when we are moving across CD or AB, it is not same. So that is why physical properties are not same in all the directions. That is why it is anisotropic. Though there is long range order, don't confuse these two things. Crystalline, it is true that there is long range order and arrangement, but they are anisotropic in nature. On the other hand, amorphous, there is random arrangement, but they are isotropic like liquids. Fine. Heat of fusion, that is the heat change for fusion, there is definite amount. So whenever there will be change from solid state to liquid, there will be a particular amount of heat change. But this is not the case with amorphous solids. Here heat of fusion, it is not definite. Fine. Melting point, there is sharp melting point. So as heat of fusion, it is definite, so there is sharp melting point. So suppose the melting point is, if we say, we can say it properly, 100 degree. So suppose it is 100 degree melting point. So when we are reaching 98, still there will be no melting. Only when it will reach 100 degree, then there will be melting. But if it is amorphous, it gradually softens over a range of temperature. So what it means? It means that if the that is in the case of crystalline, what we have seen, when it is 100 degree, when we reach 99, still it will not start melting. So there will not be any range. But in case of amorphous, maybe it will start melting at 97 and it will continue up to 103 or like that. Okay, so there will be a particular range. There is no sharp fixed melting point. So this is another difference between crystalline and amorphous. Now we will focus only on crystalline solids, because whatever solid we see around us, mostly it falls under crystalline solids. So that is why crystalline solid we will focus, and depending on different types of intermolecular forces that hold the constituent particles together, there is some classification. Now what are these intermolecular forces? These forces are van der Waals forces, ionic bond, covalent bond and metallic bond. So you can also say that it is ionic force or covalent force or metallic force. Fine. So mostly it is bond, that is why we have written it in this way. Now when it is van der Waals force, then there is a specific type of solid. Now under van der Waals force, there are some different types of van der Waals force, like dipole-dipole interaction. Then we have induced dipole interaction, dispersion force, London force, etc. Okay, and when van der Waals forces are present, then there is one type of solid. When ionic bonds are present, that is electrostatic attraction between ions are present, then one type of solid. And when so here we will see different types of crystalline solids: molecular solid, ionic solid, covalent solid and metallic solid. So molecular solid is that solid when there are van der Waals forces are present. That is the first type of forces, and it depends on what type of van der Waals forces are present. Depending on that, there may be non-polar molecular solid, polar molecular solid, or hydrogen bonded molecular solid. Okay, and next is ionic bond. So when there is ionic interaction present between ions, so obviously as we are saying ionic bonds, ions must be present. Okay, so ionic bonds, that will result ionic solid. Okay, then if there is covalent interaction, that is covalent bond is present, then we will have covalent crystalline solid, and at last the number 4, if there is metallic bonds present, then it will be metallic solid. Okay, so these are the 4 types, but first is molecular solid, that we will discuss in detail, and under this category we have 3 more classification: non-polar, polar, and hydrogen bonded. Classification of molecular solid. So here we have under molecular solid 3 types. So these 3 types are non-polar, polar, and hydrogen bonded. So we will compare these 3 on the basis of their conducting property, their melting point, what is their that is mostly they remain in liquid state or gaseous state. Obviously it is solid state, but under normal condition whether they are staying in liquid state or gaseous state, that we have to see. We can convert any liquid or gas if we decrease the temperature, but under normal condition what is their natural state, that we will compare, and what type of intermolecular forces are present. So non-polar molecular solid, they are insulator of electricity. So for conducting electricity there must be presence of free ions or electrons, free electrons. So if that is not present, obviously it will be insulator of electricity. Similarly the polar molecular solid, that is also insulator of electricity, and hydrogen bonded, that is also same. So these 3 are, sorry, this point is common for all these 3. Then if you consider melting point, it is very low melting point. So that is the reason usually they remain in liquid state or gaseous state at room temperature and pressure. That is under normal condition they remain in liquid state or gaseous state. But in case of polar and hydrogen bonded, this is also low, but see here it is very low, but compared to non-polar solid melting point, their melting point is to some extent high. Most of these are gaseous and liquids under room temperature and pressure. So here also we have gas and liquids, but it may be that this liquid and this liquid, if we consider, if its melting point and if you compare its melting point, that may vary. So though we are saying that it is very low melting point and it is low melting point, and both are remaining in liquid state and gaseous state, but there may be variation in the melting point and boiling point of the liquids. Fine. And the last one, that is they are volatile liquids and soft solid. Now we have solid, but it is very soft solid, because see all these interactions, that is non-polar interaction, which is basically London forces. We will come to that point, what is London forces. Then dipole-dipole interaction, then hydrogen bonding. Fine. All these are not very strong forces, so that is why they are not typical, that is solid. By solid what we understand, they are not that type. So what is London forces? This is actually induced dipole. That means the molecules are actually non-polar, but if there is some polarity generated, then there may be some forces. So suppose we have helium atom, okay, there is nucleus is here and electrons are present in this way, 2 electrons. Now suppose under one condition, if there is asymmetry in the structure, suppose now nucleus is here and electrons are one side, so now there will be positive charge left hand side and negative charge on this side. So under normal condition it is obviously non-polar, it is non-polar, but polarity may be induced when this symmetry is lost. Now another, this is one helium atom Now if there is another helium atom where the nucleus is here, so positive charge will be here and the negative charge is here. So now there will be, sorry, it will be positive here and negative this side. Electrons are this side, so there will be negative. So now there will be attraction between this negative charge and positive charge. So this is another helium atom. So this type of interaction is basically present, that under certain condition, if there is asymmetry in the electron distribution, then there will be some polarity generated, that is induced polarity. That is natural polarity is not present, it is induced polarity. Then there will be plus minus charge, and now there may be interaction between the negative and positive charge. So that is why it is also known as induced dipole interaction, or London forces. Another name we use, dispersion forces. Examples under this category is hydrogen, argon, mostly the noble gases fall under this category, then iodine, helium, etc. Fine. Now when it is polar, so when it is polar, there is dipole interaction. So for example, solid HCl, solid CO2. Now see, we have written solid HCl. Why? Because under normal condition it is not solid, but when we keep it at low temperature, then it will be solid, and then it will act as polar molecular solid. So that is why we have written solid HCl. Similarly, solid CO2. CO2 under normal condition is gas, but we can make it solid by decreasing temperature. So under that condition, it will behave as polar molecular solid. So suppose we have HCl. Now HCl, it is polar. Why? Though there is covalent bond, but still it is polar because chlorine is more electronegative than hydrogen. So there will be partial positive charge, and over chlorine partial negative charge. Now another molecule, if we draw del plus, del minus, so there will be interaction between these two. So this is dipole interaction, because this is one dipole, another HCl molecule, that is second dipole. So there is interaction between two dipole, that is why it is dipole interaction. And compared to the previous interaction, that is London forces, these forces comparatively stronger. Next, that is the third one, the last one is hydrogen bonding. So hydrogen bonding, it mainly occurs between hydrogen and fluorine, oxygen or nitrogen. So these three are the most electronegative elements in the whole periodic table, right? So that is why it is highly electronegative, and interaction between H of one molecule and F of another molecule may happen. So for example, if we consider water as solid, that is ice. So this is water molecule, and if I write another molecule, so here interaction between oxygen and hydrogen of another molecule may take place. So this is known as hydrogen bonding, and this type of hydrogen bonding, very good example is solid H2, that is nothing but ice. Fine. So these are the three categories under molecular solid. Next category is ionic solid. So ionic solid, it is based on ionic bond. So what are some common characteristics of ionic solids? So here we have a picture which is sodium chloride, simple table salt. The constituent particles here are ions of opposite charges. So now we have presence of ions in the ionic solid. So that is why we are calling it ionic solid. And the number of ions that surrounds a particular ion of opposite charge is called coordination number of the ion. So what it means? So suppose we have one ion, and surrounding it, if there is 1, 2, 3, 4 ions surrounding this ion. So what we will say? What is the coordination number of this ion, which I am making it solid color? So this, it has coordination number 4, because 4 ions are surrounding it. So such solids are formed by 3-dimensional arrangement of cations and anions. So obviously when we are talking about ions, there will be positive ions and also negative ions, and as they are oppositely charged, there will be strong electrostatic force. These solids are hard in nature and also brittle in nature, they can break. and they have high melting point and boiling point because there is strong electrostatic force. So to melt them we have to provide very high temperature, and to make them gaseous we have to provide very high temperature. They are generally soluble in polar solvents like water. Now we know that like dissolves in like, that means water is also polar. So that is why this molecule being polar, because it is ionic, so there will be some similarity in character. So that is why it can be soluble in water or any other polar solvent. If we take, then also it will be soluble. They are electrical insulator in the solid state. So electrical conductivity is not present when they are solid state, because now the ions, they cannot move, their position is fixed. But if it is in molten state or in aqueous solution, now the ions, their interaction between the ions, it will be weak, so they can now move freely, and when they can move freely, only then they can conduct electricity. So that is why when it is in solid state, they will not conduct electricity, they will be behaving as insulator. But when it is in molten state or aqueous solution, they will conduct electricity because now they are free to move. Some examples are sodium chloride, zinc sulfide, magnesium oxide, etc. So here we have the example of sodium chloride. So this is the anion because it is larger in size, and this is cation. Okay, so you can see there is particular arrangement, orderly arrangement. Okay, this is the second one. Under molecular solid, covalent solid, that is the third one. Some common characteristic of covalent solids we will see here. Wide variety of crystalline solids of non-metals. So now you can see that these covalent solid, they are mostly, we can see in case of non-metals. Very good example is carbon. Okay, so here it result from the formation of covalent bonds. So obviously we are saying covalent solid, so it will have covalent bonds between adjacent atoms throughout the crystal. So these covalent bonds are very strong and directional in nature. That is why atoms are held very strongly at their positions and they are very hard. Okay, so covalent bonds, it is very strong and directional. Atoms will be held very strongly at their position and they are very hard in nature. Now they are poor conductor of heat and electricity because there is no free ion or free electron. So that is why poor conductor of heat and electricity. They cannot conduct thermal energy and electrical energy. They have extremely high melting point and may even decompose before melting. So as the melting point is very high, so before reaching the melting point, it may decompose. They are insulators and do not conduct electricity. Okay, so they are poor conductor of electricity. We have already said that here. So they will be insulator and will not conduct electricity. Now very good example of covalent solids are silicon carbide, diamond, graphite, aluminum nitride. Okay, so graphite and diamond both are actually allotropes of carbon. So diamond is basically very hard, as we have seen in this property. Okay, and they are not conductor of electricity. But unlike diamond, in case of graphite there is some exception. So why there is some exception and what are these exceptions? Graphite is actually very soft and they can conduct electricity. So this is completely different types of behavior it is showing, right? So why it is so? Structure of diamond, if we see, there is covalent bond and between the atoms. Okay, but if we look at the structure of graphite, here surrounding each atom, if we consider the number of atoms attached with this atom, it is 3, 1, 2, 3. But if you look at diamond, then each atom, there is 4 atoms surrounding it. Fine. That is expected for normal carbon, because for carbon we know it is tetrahedral arrangement, 4 bonds are there. But graphite 3, that is out of 4 valence electron, because carbon is 2s2 2p2. So out of 4 valence electron, it will use only 3 electrons for bond formation with these 3 another carbon atoms. But the 4th electron, that will be remaining between these 2 layers. So this is one layer, this is another layer, and this 4th electron that is free to move between these layers. And as this electron is free to move, they can conduct electricity. And between each layer there is weak binding forces. So that means one layer can easily slide over another layer. So that is why we can write with pencil, because pencil is made of graphite. It is soft. If it is very hard, how we can write? Fine. So the layers are gliding over each other. That is why they are very soft, and the electrons are free to move in between these layers. The 4th electron, that is not rigid, that is free to move. So that is why they can conduct electricity. But except these 2, other points are fine. So only these 2 points for graphite, this is the exception. But if we consider other points, it is fine. So these are some examples of covalent solids: silicon carbide, diamond, graphite, aluminum nitride, etc. Okay, and our last category, metallic solid. So in metallic solid there will be metallic bonding, and from the name you can understand that it will be mostly the metals. For example, silver, copper, iron, etc. So here interparticle forces in this type of solids, they are metallic bond. The metal atoms occupy fixed positions, but their valence electrons are not fixed, they are mobile. So as if the metal ions, you can see in the picture, as if they are floating in the sea of solvent, in the sea of electrons, because these are electrons. So you cannot say that this electron is belong to this atom or this electron belongs to this ion. No, we cannot say that freely, because this electron may be coming from this cation. We cannot say that exactly, because they are free to move. Okay, so there is no fixed electron for each cation. They are actually floating in the sea of electron. So electrons are mobile. So that is the reason they are very good conductor of heat and electricity. We all know that metals are very good conductor of heat. That is, if we suppose we have a metal, any metallic thing, and if we are giving thermal energy on one point, then we can feel the thermal energy after some time on the other side also. So they can conduct thermal energy. They generally range from soft to very hard. So these metallic solids, it may be very soft or it may be very hard. They are malleable and ductile. So malleable, this is a property. So what is malleability? Malleability means for this property they can be, that is the metals, it can be made into thin sheet. And ductility is another property for which they can be, that is from metals we can make thin wires. Okay, so these are the 2 properties that are present for metal, and that is why there is so much application of metal. Fine. They possess bright luster, for which they are also used as ornaments. They have high melting point and boiling point. Okay, so this metallic bonding, it is strong, so that is why there is high NP and BP. So these are the examples. Okay, so these are the 4 categories under crystalline solid. The first one, it is where van der Waals forces are present. Then what we have seen, it is molecular solid. Then we have seen ionic solid, covalent solid, and metallic solid. Okay, next is crystal lattice and unit cell. So lattice, this term we have already seen. Now crystal lattice, obviously it is for crystalline, not for amorphous. So crystal lattice, it is 3-dimensional representation of constituent particles. Now these constituent particles, it may be atom, it may be ion, it may be molecule. Okay, so 3-dimensional representation of constituent particles, and you can consider these particles, that is atoms, ions or molecules, as points in space arranged in a specific order or pattern. So this order or pattern, that is specific for each substance, and each point in a lattice is called lattice point or lattice site. So please keep it in mind because we will use this term later. Lattice point, lattice site. Yes, it is atom science or molecules, but in general we will call them as lattice point or lattice site. So in the picture you can see all these are lattice points, and if you consider this square, this green square, it is not actually square but square like, then it is the repeating unit. That is, by repeating this unit cell we can make the whole arrangement. Okay, so as if this large structure, it is the repetition of this small part, so that is why it is called unit cell. Okay, so this is the smallest portion, smallest similar portion that is repeating again and again. Lattice points are joined by straight lines to bring out the geometry of the lattice. So here you can see lattice points, they are joined to each other by straight line. The smallest possible portion or part of the crystal lattice which repeats itself in different direction of the lattice is known as unit lattice. Okay, for example this green portion, we can construct the entire lattice by translational displacement of the unit cell in the three-dimensional. Translational displacement means, suppose if it is unit cell, it can move only in this direction, that is translational, straight, or it can move like this, then this. So this is translational displacement. So that is the all about unit cell and crystal lattice. Now there is classification of unit cell. Unit cell may be different types. So what are the parameters of a unit cell? Parameters of unit cell. Now look at this picture. Here this parallelogram, it is actually the unit cell. Here we have A axis, actually it is A side, B side, and another is, the third one is C. So as if it is XYZ axis type. So A is one axis, B is another axis, C is another axis. Now the angle between A and B is gamma, angle between A and C is beta, angle between B and C is alpha. Okay, so these are the 6 parameters by which we can specify the unit cell. Okay, so it has 3 edges A, B, C and 3 angles possible between A, B, BC and CA. These are alpha, beta, gamma between the respective edges. So unit cell is characterized by these 6 parameters. Okay, so if we know these 6 parameters, we can easily classify that under which category the unit cell will fall. Okay, now unit cell, it may be, first we can divide it in primitive and centered, and under centered there is 3 types: body centered, face centered, end centered. So what is primitive unit cell? So in this type of unit cell, you will see that the constituent particles, they are located only at the corners of the lattice. So there are 8 corners and 8 lattice. So this is very simple. This is the most simplest unit cell that is possible. That is what is known as primitive unit cell. Okay. Next we will see centered unit cell. So in centered unit cell, in this type of unit cell, constituent particles are located at corners, that we have already seen in case of primitive. But here some extra positions are also occupied as well as other positions. So now we will see that a lattice site that is present at corner as well as some other positions also. Now depending on this other position, there will be 3 more categories. Body center. So from the name you can understand that one constituent particle will remain at the body center. So this is the body center. Yet, yes, it looks different. So this is one type of atom, ion or molecule, or this may be another type. So that is why it is different. But here in the body center there will be a particle, and these corner particles are already there, just like primitive. So that is common. So as if after primitive unit cell we are adding something more. It's like that. Then we have face center. Now here from the name you can understand how many faces are there. Obviously 6 faces. So this is one face, that is this one. Then we have in this right hand side face, this is the lower face constituent particle. This is the left hand side face, and this is the front face, this is the back face. So total 6 faces are there, so that is why 6 atoms are extra. 6 faces, 6 more constituent particles are present. That is beside these corner atoms, they are already there. And the last type is end-centered. So in end-centered, in this type of unit cell, one constituent particle is present at the center of any 2 opposite faces. So any 2 opposite faces, here we have taken this face and we have taken this opposite face. But it also may be like it is present at this side and this side, or the front face and the back face. Okay. So any 2 opposite faces, there will be a particle. So it is also like face center, but all the faces are not covered. Only 2 opposite faces are covered with the constituent particle. Now, depending on these parameters that we have seen in the previous slide, that is A, B, C, the 3 edges and 3 angles between the respective edges, depending on this variety of A, B, C and alpha, beta, gamma, we can have 7 types of unit cells. So what are these 7 types of unit cells? The first one is cubic, and this cubic, it may be primitive, body centered and face centered. So under cubic there is 3 types, and here edge length, all edge lengths are same, and the angles, all angles are 90 degree. Okay. So this is the example, the first one. Here the conditions are mentioned. NaCl, copper, ZnS, these are the examples. The next type is tetragonal. Under tetragonal, it may be primitive and body centered. So two types possible under tetragonal. Here 2 edges are same, but the third edge is not same. Okay. So these are the conditions mentioned, and here just like cubic, all these are 90 degree. Examples are also mentioned in the last column. Third type is orthorhombic. Now under orthorhombic there is primitive, body centered, face centered, end centered. So it's total 4 types. Here all the edges are different, but all the angles are same. Okay. Example, rhombic sulfur. This is one allotrope of sulfur. There are different types of sulfur: monoclinic sulfur, rhombic sulfur. So this is rhombic sulfur because it has orthorhombic structure. From that structure the name is rhombic sulfur. Barium sulfate, KNO3. Next is hexagonal. So hexagonal, here 2 edges are same, the third is not same, and only one type is possible here. The first 2 angle 90 degree, but third angle it is 120 degree. So this is 120 degree. Okay, so you have to focus only on this particular region, not the whole structure. Just focus on this part. Fine. Next is rhombohedral. So rhombohedral, under this we have only one type. Here all the edges are same, all the angles are same, but they are not equal to 90 degree. But they are having same value. Whatever is the value, it is same, but it is not 90 degree. Example, calcium carbonate, HGS. Monoclinic. Under monoclinic we can have primitive and end center. So 2 types. Here all the edges are different. 2 angles 90 degree, 1 angle not 90 degree. So this sulfur, it is also known as monoclinic sulfur. You can call it monoclinic sulfur. And monoclinic, here this is the condition. And triclinic. Under triclinic, only 1. Now if we add all these numbers, you will see 3 plus 2 5, 5 plus 4 9, 9 5 14. So total 14 types if we consider all these numbers. So triclinic, all the edges are different, all the angles are different, and they are not equal to 90 degree, and even they are not equal to each other also. Okay, so this is the triclinic structure. Example, H3PO3, copper sulfate, 5H2. Okay, now we will see that how we are getting these 14 types. That is, under cubic there is 3, under tetragonal 2, under orthorhombic 4, hexagonal 1, rhombohedral 1. You will see there is another name for rhombohedral. We will also see that, because in some books you may find it is mentioned in a different way. And monoclinic we have 2 types, and triclinic only 1. So 14 possible 3D Bravais lattice. So this name is basically coming from the scientist who discovered it. Okay, Bravais lattice. So here you can see under cubic we have primitive, body centered, face centered, no end centered. Okay, that we have already seen in the previous slide. Here no end centered, only 3 types. Then under tetragonal only 2 types. So this is tetragonal. Here we have 2 types only. That is primitive. This is the column of primitive, second column end centered, third column body centered, last one face centered. So here we have primitive and body centered, only 2. Under orthorhombic, total 4 types: primitive, end centered, body centered, face centered. Under monoclinic, 2 types: primitive, end centered, primitive, end centered. And for hexagonal, triagonal, triclinic. So this triagonal, that is also known as rhombohedral. If you look at the previous slide, here we have rhombohedral. You can also write it triagonal. So under hexagonal there is only 1 type, so that is why it is not mentioned. Okay, hexagonal, triagonal, triclinic. So if you add all these numbers, so here we have total 3, this is 2, here 4, 2, and here we have total 1 plus 1 plus 1, 3. So 3 plus 2, 5, 5 plus 4, 9, 9 to 11, 11 and 3 is 14. So total 14 structures possible. Fine. Closed packed structures. What is closed packing? The packing of constituent particles occurs inside lattice in such a way so that there is less amount of void. That means they can occupy maximum available space in the lattice, and there will be minimum amount of vacant space, and this vacant space is known as void. So that is why this type of packing is known as close packing, and the structures will be called close packed. Okay, so there is ordered arrangement, and this ordered arrangement happens in such a way so that there is minimum amount of vacant space available. Now, when we are considering this close packing, there is important assumption. And what is this assumption? So that to make the matter simple, that is, when we will do the analysis, if we consider the ions and molecules and atoms as hard sphere of identical shape, then only it will be easier to explain. So that is why, though we know that ions, molecules, atoms, they are actually not hard sphere or identical shape, but for simplicity and for the ease of analysis, we consider them, we assume them as hard spheres, and all of them are identical in shape. So if there are 2 same ion, we will write it similarly, that is, we will draw it similarly. Close packing can be done in 3 ways, and that depends on the dimension. If it is 1 dimensional, then it is one dimensional close packing. If it is two dimensional, it is two dimensional close packing, and three dimensional close packing, which is the actual real structure. Because when we consider the crystal structure, obviously it is three dimensional, it cannot be one or two dimensional. So in one dimensional close packing, how it will look, it will be, okay, we will come to that point, but before that, here you can see some pictures of close packing. This is single layer, two layer and three layer. We will come to that point in detail, what is HCP or CCP, but these are some of the examples of close packing. From the structures you can understand that they are tightly packed with each other and there is very minimum amount of space that is vacant, right? These are the vacant space, but this is very minimum. So here first is one dimensional close packing. So what is one dimensional close packing? Actually it is very simple. So even if we do not consider any picture, you can just imagine it as if it is like one row, simply one row. So this is one dimensional, it is simply moving in this way. Okay, so if we consider this atom or particle, whatever, then what is the coordination number? Here coordination number will be 2. Okay, 1 and 2, because surrounding this colored atom there is only 2 particles. Fine. Two dimensional close packing. Now two dimensional close packing, it may be two types. One is square close packing, another one is hexagonal close packing. Okay, so what is square close packing? It is also known as AA type. So in the picture, if you see, suppose this is the first row, that is one dimensional. Then when we are placing the second row, the atom that is exactly on the first particle. So here the second row may be placed in contact with the first one in such a way that the sphere of the second row, so suppose I am writing here 1 because this is the first row and this is second. So see, each second particle that is in the second row, the particles are exactly on the first one, right? And the spheres of the two rows are aligned horizontally as well as vertically. That means if we move in this direction, then there is similar type of arrangement, and if we move this towards this side, so both sides are actually similar. Whether you move horizontally or vertically, that does not matter. Both sides they are looking same. So here the space that is available between 4 particles, this is square in shape, right? This vacant space is square in shape. And if you consider a particular atom, suppose if I consider this one, surrounding this there are total 4 atoms, that is not atoms, it is better we say constituent particles. So for this constituent particle there are that is 4 constituent particles are touching it, direct contact. So what we can say here, coordination number is 4. Okay, and here you can remember that why it is close packing. You can remember that here the void is square in shape, so that is why it is close packing. So in this way you can remember both the structure and name together. Okay, let me tell you one thing, that it is also called AA type. Now why it is so? Because if you consider the first layer and the second layer, it is actually similar type, so that is why all this will be A. It is AA type. Next type is AB type or hexagonal close packing. Now see, if this is the first row, 1 1 1, then 2 2 2. So when we are arranging the second layer, this is the second layer, this is the first layer. So here the particles we are placing in the depression of the 2 particle of the first row, okay, in this depression. So the second row may be placed above the first one in a staggered manner, such that its spheres fit in the depression of the first row. So these are the depression of the first row, and in each depression there is presence of the second particle, that is particles of the second row. Now if you compare the vacant space, here you can see the spaces that are vacant, that is void, basically void. Less free space, here it is mentioned, this is basically void. So this void, it is very less in the second structure. Okay, and here what is the coordination number? If you consider any particular particle, surrounding this particle there is 1, 2, 3, 4, 5, 6. 6 particles are present. So here coordination number will be 6, and here coordination number 4. Okay, so obviously as there is less free space, less void, this packing is more efficient than the square closed packing. Obviously that is very clear from the picture also. Here vacant voids are very large in size, but here voids are very small. Coordination number is very high, so here packing is more efficient compared to square closed packing. So here in case of the second one, remember this is AB type. Why it is AB type? Because if you consider the first row as A, the second one we will call B because it is not similar. And now if you look at the third layer, this is basically same as the first layer, right? That is why it will be again A, then B, because the fourth layer you can find similarity with the second layer. So in this way it will move, it will go on. Okay, AB, AB. So that is why it is also known as AB type. So this is two-dimensional closed packing. Now the main important thing is the three-dimensional closed packing, because in reality, that is when we consider actual real lattice or crystal, they take place, that is the formation of this real lattice can take place through three-dimensional closed packing. Now here also we have two ways. The first one is number 1 point, three-dimensional closed packing from two-dimensional square closed packing. So remember in last slide we have already seen two-dimensional closed packing. Okay, so two-dimensional square closed packing, because two-dimensional there is two types. One is square closed packing, which is AA type. Another one is AB type. So when starting from two-dimensional AA type, what we get, that we will see now. So how we can do it? It can be done by placing the second square closed packed layer exactly above the first one. And in this closed packing, the spheres are aligned properly in horizontally and vertically. Okay, so look at this picture. Here, this is three-dimensional arrangement, and if you consider each layer, okay, so the upper layer, that is placed exactly above the second layer. Okay, so in this closed packing, spheres are aligned properly in horizontally, vertically. So when whether you move vertically or horizontally, you will find similar kind of arrangement. Similarly, by placing more layers one above the another, that is if we carry on this process, we will get simple cubic lattice. That is if you consider only 4 particle here, and behind this 4 particle there is another 4 particle. So together this 8, it will consist, it will make simple cubic lattice. And the unit cell of this simple cubic lattice is called primitive cubic unit cell. Remember, primitive cubic unit cell we have discussed. It is like this. Primitive unit cell, there is presence of particle only at the corners. So total 8 corners. Okay. So remember, primitive cubic unit cell, this is the unit cell of this type of three-dimensional closed packing, which we are making starting on the basis of AA type that we have seen already in case of 2 dimension. Now the next one is 3-dimensional closed packing Now starting from hexagonal close packing or AB type close packing. So this is the picture of AB type close packing that we have already seen, right? Now suppose if this is one layer, if we place another layer above it, that is stacking the second layer over the first layer, okay, in a staggered manner, then we will get this type of structure. Now suppose we are looking at this structure from this side, but if you place your eye position here, if we look from this side, then the picture will be like this right hand side picture, okay. Just if you look from this side, if this is our eye position, now we will see this type of arrangement. So here the deep blue colored this circle, that is for the layer which is towards us, and the light blue colored circles, that is away from us, okay. So when it is placed in this condition, in this way, that is staggered manner, we will get two types of void. Types of void in three-dimensional close packing. So one type of void is, see, it is known as tetrahedral void, because if you just focus on this part, why it is tetrahedral void? Because if you consider this void, surrounding this void there is total 4 particles, 1, 2, 3, 4. So that is why this type of void is known as tetrahedral void. And there is another type of void, if you consider this void, it is known as octahedral void. Now why it is so? Because surrounding this void there is total 6 particles, 1, 2, 3, 4, 5, 6. That is why this is known as octahedral void. So there are two types of void, tetrahedral void and octahedral void. And remember this may be a question also, that if there are n number of close packed spheres, then how many octahedral voids and how many tetrahedral voids will be there. So here these circles, if you consider, if there are total n close packed sphere, it is not circle actually, it is sphere because it is 3-dimensional, then octahedral void will be same as the number n. But if it is tetrahedral void, it will be double. Now it is also clear from this picture, because see here this tetrahedral void, this is 1, this is 1 and third, but for we are getting here 3 tetrahedral void row, but we are getting only 2 octahedral. So octahedral void, they are always lesser in number. Remember, octahedral it is 2n, octahedral is n because it is lesser in number compared to tetrahedral void, and tetrahedral void it is double that of octahedral void. So this may be a question, that what is the number of, if the value of n is given, then what is the number of octahedral voids, what is the number of tetrahedral voids, okay. And why we are discussing this type of void? Because we have not done the layering till now. Because when there are two types of void, based on what type of void we are using for placing the third layer, because until now we are just at the second layer, okay, and in the second layer we can see two types of voids. Now depending on these two types of voids, if we place the third layer on tetrahedral void, then there will be one type, and if we place the spheres on the octahedral void, there will be another type, okay. So stacking the third layer over the over the second layer, it is not first, it is the second layer. So there are two possible ways of placing the third layer over the second layer: by covering the tetrahedral void, this is one method, and by covering the octahedral void, that is the second method. So if now we have the same picture again, so that we can compare it. So when we are placing the third layer on tetrahedral void, basically it will be like this. Suppose the red color that I am drawing here, this is for the third layer. So basically the third layer, you can see it is exactly like the first layer, that is this light blue color, this is number 1, this is number 2, that is second layer, and the red one that I am drawing now, this is third layer. So basically the third layer is the repetition of one. So if the first I am writing as A and the second layer is B, then third layer will be A again. So it is AB type. But if we are placing the third layer over the octahedral layer, so it will be like this. Now see, when we are placing the third layer over the octahedral void, it is not the repetition of this first layer. So first layer is 1, this is 2, and this red color that I am drawing now, this is 3. So now 1, 2, 3, it will be A, B, C type. It is not same that we have seen in case of the previous one. So when it is we are covering tetrahedral void, basically we will get HCP. This type of structure is known as HCP, hexagonal close packed. And when we are placing the third layer on octahedral void, basically we are getting FCC, that is face centered cubic lattice. It is also known as CCP, cubic close packed or face centered close packed. Okay, so the ABC type we are getting when we are covering the octahedral void. Okay, in this way. So if I draw 3 such, another is this octahedral void, so you can see this is the third layer. Okay, that is, if you consider this green layer, this is actually the third layer of when we are covering the octahedral void. And now there is some gap, but if you bring them closer, it will be, now it will look like this. Okay, so this is A, B or small a, B, then again A, then again B, it will go on, and this is A, B, C, then again A, B, C. In this way it will move on. Okay, so in the previous slide we have seen 3-dimensional close packing from hexagonal close pack. This is the second type, and in this second type, depending on whether we are covering the tetrahedral void or octahedral void, we can have 2 more types, and these 2 more types is HCP and FCC, or it is also known as CCP. Okay,